All right, let's dive right in. We're on the hunt for a theory of everything, right? But that whole quest just slams into a wall when you ask one simple but impossible question. What is quantum gravity? Today, we are going to explore a really fascinating new idea called dynamic vacuum field theory. And get this, it suggests the answer isn't about particles or strings at all, but about the very fabric of space itself.
Okay, so this is the absolute heart of the problem. You've got quantum mechanics on one side, telling us a particle can be in a superposition, smeared out like a wave, existing in multiple spots at the same time. But then general relativity comes along and says that any mass or energy has to curve spacetime, and that's what gravity is. So what gives? If the particle's in two places, does spacetime curve in two places? And what on earth happens when you measure it and it suddenly snaps to just one location? Our two best theories of reality they don't speak the same language. They can't answer this.
So this new way of thinking, dynamic vacuum field theory, or DVFT for short, it proposes a total shift in how we look at this. It argues that we've been looking in completely the wrong place. The answer isn't some hidden property of matter. It's in the thing we've always taken for granted, that supposedly empty space all around us.
So let's meet the hero of this story, the vacuum. Now, DVFT says we have to stop thinking of the vacuum as this empty, boring stage where things happen. Instead, think of it as a dynamic, physical substance. It's the literal substrate of reality, and it has its own properties, its own rules.
The best way to picture this is to imagine the vacuum is like the surface of a huge, perfectly still pond. It has a certain tension, right? A kind of stiffness. In DVFT, we call that its amplitude. And it also has this perfectly ordered, uniform structure. We call that its phase. The whole idea of this theory is that everything, particles, forces, gravity, the whole shebang, they're just disturbances in this underlying field.
And this slide right here, this is the paradigm shift. The old view on the left, it says matter tells spacetime how to curve. But the DVFT view on the right completely flips that. It says matter is just a disturbance in the vacuum. Gravity isn't some weird force acting from a distance. Gravity is the physical reaction of the vacuum to being disturbed. The vacuum itself becomes the thing that carries gravity.
Okay, so here's the core equation of the theory. Now, don't let the symbol scare you. The idea behind it is actually pretty straightforward. It just says that at every single point in space, the vacuum is described by two numbers. That first one, rho, represents that stiffness we talked about, the vacuum's energy density. Think of it as how much the vacuum resists being poked. But the second one, theta, that's the phase. And you can think of that as the local structure of the field. And it turns out this theta is the key. It's the variable that holds all the information about gravity's geometry.
So we have this new picture of a dynamic physical vacuum. Let's go back to our original puzzle. What about that particle in a quantum superposition? How does DVFT explain its gravity?
Now this is absolutely crucial. In DFT, a quantum wave isn't the particle itself getting smeared out, no. It's a coherent, organized ripple in the phase of the vacuum. The particle's energy creates this gentle, wave-like disturbance in the vacuum structure. And that ripple holds together as long as the system stays coherent, as long as the pattern remains unbroken.
And this quote just nails it. Because the source of the gravity, this coherent ripple in the phase, is spread out, the gravitational effect it creates is also spread out. It's not gravity in two places anymore. It's one single complex gravitational pattern that's distributed over the whole area of the ripple. And because it's a wave, it can interfere with itself, which is exactly the weird behavior we see with quantum particles.
Okay, that explains the wave. But what happens when we actually look at the particle, when we measure it? How do we go from that gentle, spread-out ripple to the sharp, localized gravity of a single object that we know and love in our everyday world?
Well, in standard quantum mechanics, wave function collapse is this big mystery. It's treated like someone just flips a switch. It's a mathematical rule without a real physical cause. But DVFT says, hold on, it's not magic. It proposes a real physical mechanism for this transition, and it's all based on the properties of the vacuum itself.
So here's the story. When a particle is in a superposition in two different places, it's basically asking the vacuum to hold two different, competing gravitational patterns at the same time. This creates a kind of strain, an energetic tension in the vacuum field. And as the particle gets more massive, or the distance between its possible locations gets bigger, that tension just builds and builds until the vacuum reaches a breaking point.
And the theory gives us a precise condition for when that break happens.
On the left, that E theta represents the energy cost of that structural mismatch. It's the amount of stress the superposition is putting on the vacuum. On the right, that rho zero is the vacuum's fundamental stiffness, its resistance to being pulled out of shape. So the equation is basically saying that when the stress of holding those competing ripples becomes too much for the vacuum's inherent stiffness, coherence breaks. The vacuum field literally snaps and relaxes into the easiest, lowest energy state it can find, which is a single, localized particle. And that is wave function collapse in DVFT. It's a physical event.
So, we've seen how this theory can describe both the weird quantum wave and the familiar classical particle. Let's just put it all together now into a really clear side-by-side comparison. It's almost like a new dictionary for these concepts. This table is a fantastic summary. Let's just walk through it. First up, the vacuum state itself. In the wave state, the vacuum has this coherent, spread-out pattern. After collapse, it's localized into a single pattern. Next, the gravity source. Before collapse, gravity comes from these distributed changes or gradients in the vacuum's phase. After, those gradients get super concentrated in one spot. And that leads directly to curvature. What starts as a single complex pattern that can do all that quantum interference stuff becomes the familiar, classical, localized curvature of an object. And finally, the trigger. The change doesn't happen because of some abstract measurement. It happens because of a physical event. The vacuum's coherence breaks when that stress threshold gets crossed.
So when you boil it all down, what this theory really gives us is a cohesive story. It's trying to replace these abstract mathematical rules with actual physical mechanisms. It suggests that the strangeness of quantum mechanics and the familiar pull of gravity are really just two sides of the same coin. They're both behaviors that emerge from one single underlying substance, this incredible dynamic vacuum.
And that's the final thought I want to leave you with, a really provocative one. What if this is right? It would mean the vacuum isn't passive, it's active, it's computational. It's the very medium that enforces the laws of physics. It would mean that the deepest secrets of our universe might not be hidden away in smaller and smaller particles, but in finally understanding the complex dynamic behavior of the space in between everything.